Hi everyone, I'm Hong Dong. I'm very honored today to present my dissertation at SIGMOD 2026. I graduated from the University of Wisconsin last year. I was advised by Professor Paris Kutris, and I now work at Microsoft's Gray Systems Lab. Now let's dive in. Join performance is critical for modern databases, and over the past decades, two provably optimal algorithms have been invented for joins. One is the Yanakakis algorithm, which is optimal for any query whose join graph is a tree or acyclic. The other is the worst-case optimal algorithm, which attains best possible runtime even for cyclic queries as well. So, does that mean the end of join algorithms? Not quite. As it turned out, this theory addresses mainly pure inner joins, and real-world queries can go far more beyond that. This dissertation tries to bring this theory into that messy reality of real-world queries. Concretely, it introduces four new join algorithms. First, for join aggregate queries, where joins are followed by group by aggregation. This is extremely common for SQL. Second, anti-join queries, which are quite common for graph subpattern matching. Third, join workloads under changing predicates, where the same structure of join is evaluated again and again in a workload, but under the hood predicates keep changing. And fourth, iterative or recursive join, which are very useful for program analysis or graph traversal tasks. For join aggregate queries, we introduce output-sensitive join algorithms. Here's an example query. This is the same query as the previous one, except for now we want x1 and x4 columns only, rather than every attribute. It turns out that output-sensitive algorithms are optimal here, whereas the Yanakakis algorithm are not. This is the first general improvement to the Yanakakis algorithm over the past 4 decades. The second is about optimizing anti-join. An example looks like this. You're asked to join RNS and then anti-join on the endpoints for x1 and x3 by t. Today, almost every database would first join RNS and then anti-join by t. We designed an algorithm that intuitively pushes anti-join down the inner join to minimize intermediate outputs. This is the first optimal algorithm covering a broad family of anti-join queries. Next, we move to join workloads under changing predicates. In this example, we have the query R join S join T. But in a workload, the predicate values of x1 and x4 keep changing. A common optimization for this workload is to materialize the entire join. So every x1, x4 request or values become a single table lookup, but that can be space inefficient. In the other extreme, every request triggers an on-the-fly query execution. One can see it as a query instance. We propose an algorithmic framework that can dial join algorithm along the full spacetime trade-off curve. For many queries such as this one, this framework refutes long-standing algorithmic conjectures about spacetime trade-offs. Finally, we look at iterative or recursive joins. We study them through the lens of Datalog, a declarative language that elegantly captures recursion. Existing join algorithms don't necessarily carry over recursive queries on their own. So, we introduce a unified recipe that lifts any join algorithm into that recursive scope. In this example, which is a single source shortest path queries written in Datalog, this recipe rediscovers the famous Dijkstra's algorithm. We instantiate this recipe in an engine we built, Flowlog. Unlike previous recursive query engines, Flowlog sits on top of differential data flow, a popular incremental API that, as it turns out, a remarkable fit for recursive queries. Out of the box, the Datalog program now runs incrementally, it scales up and down, and supports many kinds of complex queries beyond SQL. A main challenge, however, is that recursive queries are often highly volatile. Runtime behavior from one iteration to the other can be very hard to predict. So we designed an optimizer targeting specifically robustness. Flowlog reliably outperforms state-of-the-art engines on a wide range of Datalog-style workloads. It is open source and you're warmly welcome to try it out. Special thank you goes to my advisor, Paris Crutrus, for time, patience, and wisdom carrying me through the ups and downs of my PhD. And then a heartfelt thank you extend to all of you and to the SIGMOD Award Committee, to my mentors, friends, and to my family. Thank you for listening.